Okay, so this last question here, which we'll do more, is problematic, shall we say? Because the way I've learned it versus the current method is slightly different. So I'll try to do as best I can. Okay, let me just take a snapshot. There we go. So the big problem with this question is if you look, they want you to rotate around y is equal to 1. That would create a big circle here. And of course, a non-existent circle here with concentric circles moving towards the big circle. So essentially sort of a big headlight like that. When you take the whole point of integral calculus is you're finding, by doing an antiderivative, the area underneath this graph. Right here. And the problem for us is they want that area. Okay, so I'm going to go back to those weird concentric circles. Oop. And I'm just going to use one, okay? Well, I'm going to use two. I'm going to use that one, the big one, at the very end. But I'm also going to look at, yeah, the big one's a good example. As we go down these circles, and that one's not a good one. It's probably more like there. These circles get smaller, right? So the question is, when we find these things, all we're finding is the area of the circle, pi r squared, and times the distance. So knowing the distance is important, knowing what that point is here, because it's clear we start at 0 and go to this point right here. So that's the first thing you should do is find out that point. But let's discuss the circle. How do I find the diameter of the circle if integral calculus is giving me the wrong side of it? Okay, well, let's look at the diameter if we were to go all the way down to the bottom from this, which is essentially this one right here, all the way down because it goes to 0, 0. This graph, 3x cubed, goes through 0, 0. So all the way to here, it's clear the radius is 1, right? So this big circle outside is just pi r squared. R is 1. It's just pi. But as we get further, how do you calculate the diameter? I'll just get rid of all the clutter and zoom in. How do you calculate the diameter as the circle gets smaller? Right there. So right, we'll use the radius. With radius, I might have said diameter. Radius, right there. Well, we know that this is 1. And we know if we take the integral of that spot, we get the area beneath there. So to get this spot, this circle radius, would be 1 minus the integral of this, which would be minus 3x cubed. Now, a radius has to be squared too, so we have to square it. This makes sense when you put it on Desmos, right? So here's the original. Finding the integral underneath this is no good. But if you look at 1 minus 3x cubed, it becomes very clear why this will work. Because suddenly the integral will give me the area that I'm interested in. See? It's essentially has taken my original graph, it's reflected it on the other side, like that, and it's brought it up by 1. Oh boy. It's brought it up by 1 so that I can take an integral of it. If you look at the area under the blue graph, okay, I'll turn it off like this. If you look at the area we're interested in on the red graph, right, it is this area. Oh, why things won't work for me. I don't know. I don't know. It's this area. But integral calculus will only give us that area, unless we do exactly as I just did. Flip it, raise it. Just going to pull it over to one side. Suddenly, if integral calculus will give me that exact area. And that is indeed the radius of the circle as we go from 1 to smaller. But keep in mind, it's the radius of the circle multiplied by the height. That's what a cylinder is. When you break it down, all these complex calculus and math things, like rise over run or instantaneous rate of change or derivatives, our derivatives is just y2 minus y1 over x2 minus x1 when the x2 and the x1 are very, very close together. It's the instantaneous slope. Well, these complex integral graph rotation is really just making a circle and finding the volume when we make the circle cylinder. Just the cylinder changes as we go. And it's simply pi r squared times the height. That's the formula for the volume of a cylinder. The surface area of a cylinder is 2 pi r, the perimeter here, times the height. And then you have to do the surface areas of the two circles at the end. But on the tube itself, it's just 2 pi r times the height. These things are actually very simple processes made a little bit more complicated because they're hoping they've walked you the distance to this graph. So now we're going to go back to this question. Find the area enclosed. Well, I've discovered that the radius of that circle, oh yeah, my first question, as I said, how do we find this? How do we find this height? Let's see if I can, that doesn't matter. I think I don't need the graph anymore. How do we find the distance from here to here? Well, we know that the y is 1 there, and we know that the graph intercepts it right there. So that just means, when does this graph make 1? When does 3x cubed make 1? When x cubed is equal to 1 over 3. We take the cube root of that. The cube root rule, or any square root rule, means I'm allowed to take the cube root of anything being divided, the cube root of 1, to the cube root of 3. The cube root of 1 is just 1. So that means this intercepts at 1 over the cube root of 3, when x is 1 over the cube root of 3. This is also proven with Desmos. If I put y is equal to 1 here, it will show me the x point, 0.69336, which happens to be 1 divided by the cube root, which is 3 to the power of a third. It's the same value. So that is indeed, my integral goes from 0 on my x all the way to y. And it is indeed, when I flip it, the area that I'm interested in is indeed this area here as I rotate it around the graph. Right. So looking at that, now that I know that I have to do pi r squared. But I know I have to, my radius is 1 minus 3 x cubed. That's my radius. You're confused about that? Let me know. And I'll have to square it. Well, the pi is a constant, so I can take it out. I might as well find what the expansion of that. It's a squared plus 2ab plus b squared. 1 minus 6x cubed plus 9x to the 6. That's after we expand it. So that's my actual radius. That's 6x cubed, by the way. That's now my pi r squared. It's been squared. Well, that is my formula that I've used, but I have to use an antiderivative to find that, and I also have to do an integral calculus from 0 to my point that it intersects, 1 over the cube root of 3. The integral calculus says I just have to find the antiderivative of that. So the antiderivative of 1 is x. To prove it, bring the 1 down, make that a 0. It's 1. The antiderivative of that is I just raise that to 1, which is by 1, which is 4, and put the 4 down here. That's all the antiderivative is. So that one is 6 x to the 4 divided by 4. And it's a minus. Don't forget that's important. And then the antiderivative of that is that's just a 7, and then I divide it by 7. So I get plus 9 x to the 7, all divided by 7. By the way, these divisions can just be done to the numbers. I could simplify that as I want. So I'm left with this. And I've got to find it from 0. So if I plug 0 in there, I get 0. All the way to this. So this minus 0. So essentially all I have to do is find that. Then multiply by pi, because this is the r squared as we go along from 0 to 1 over square root of 3. And I also have to, what else do I have to do? Nothing. That's it. So all I have to do now that I found the antiderivative is plug in 1 over the cube root of 3 wherever I see x. Okay? So it's going to be, let's see if I can just use the same thing over here. This cube root of 3. That 3 should be smaller, but that's okay. Like that. Like that. Good. I'll just kind of get rid of this. Okay, so the cube root of 1 over cube root of 3. This, I'm going to find it to the 4. So what I'm going to do is find it to the 7, multiply it by 9, divide by that. And I'm probably just going to put it in my calculator. So let's do that. So clear my calculator, make sure my memory's clear. It's not. And I'm going to do 1. Actually, you know what I'm going to do? I'm just going to find the cube root of 3. And do 1 over. And there it is, like we did before. I'm going to add it to my memory. So I've got to do that to the power of 7. Multiply by 9. And divide it by 7. I can add it to the thing I found overall, because they're at these two, x and 9 are adding. And now I have to subtract. Open bracket. 6 divided by 4 times my thingy to the power of 4. Close bracket. Equals. And this should be my volume. Now, that's just this portion, not multiplied by pi yet. So that's just going to be pi, or this thingy, multiplied by pi, units cubed. If I were to stop there, and if your teacher likes seeing pi, this is what it would be. However, some teachers want you to multiply the pi out. And this is what it would be to 3 units here. Units cubed. So if it was liters, it would be 1.4 liters cubed. If it was liters, it would be 0.466 times pi liters cubed. I believe that's the answer. There's weird arguments that I actually have to find 1 minus this. That you're supposed to take the outer radius minus the inner radius, but quite honestly, the outer radius is 1 minus that. So I believe I've already done that. If you ask AI, you get a weird interpretation of that. And yeah, I believe that's all you have to do is this here. Confirm with your answer thing. If it's not that, then it is indeed an extra step of 1 minus x cubed, and we will discuss. However, I don't believe it's that. Let me know, and we'll cover it tonight, I guess.